So we started talking about segments and distances. We're going to talk about a few different things. We're looking for how long a line segment is. So there are a couple different ways that you can do this. All right, one is going to be our ruler postulate, which is just going to deal with a number line, basically. Okay, so we're looking at the points in a line that can be matched, okay, with real numbers. We're going to figure out the length between A and B. The distance between, so our distance between the 2 points is the absolute value of the difference of their coordinates. So that's what this is right here. We're going to take the 2 of these, we're going to subtract them. Absolute value is the distance from 0. Short terms, make it positive. Okay? So when we take a look at the first example here, we're going to find the distance between -2 and 6 on a number line. Well, using our distance formula, our distance is going to be the absolute value. We could just call this x1 and x2, okay, what we have in our formula. We're going to take the absolute value of -2 minus 6, okay. We know that -2 minus 6 is going to give us absolute value of -8. And just make it positive. If it's already positive, get rid of the absolute value symbol, okay. And so our distance is going to be 8. The way you look at it with a number line, okay, you can count. You can simply just count them, all right? But what we're going to do is we're going to also take a look at the same formula here. So we're going to take between P and Q. So between P right here, which would be about -3.5, and Q, which is right at 2. We're going to take the absolute value of that -3.5. We're going to subtract the -2, okay? Remember that this right here is going to end up turning into a plus. So when we take -3.5, we subtract -2, we're going to get -1.5. So then our absolute value tells us what is the distance from 0 to here. It's 1.5 units. Absolute value will always be a positive number. Okay? If we take a look, we go, okay, let's see. From here, we've got 1.5. Well, that's exactly what this showed us, right? Let's take a look at from Q, which we already know is -2, to R, which is at a positive 2.5. So we'll take the absolute value of that -2 minus just a positive 2.5. We're going to find out that when we plug in the calculator, -2 minus 2.5 is -4.5. But again, the absolute value bars right here tell us make it positive. So our distance is going to be 4.5. Distances are never negative. You cannot walk backwards 5 feet and say, I walked -5 feet. It does not work that way. You just walked 5 feet, the distance of 5 feet, you just chose to walk it backwards. Okay? So again, if you take a look here, we're going to go 1, 2, 3, 4.5. Right? So you can look at that's how we look at it with the number line. Last, we'll look at P over here at -3.5. So we have absolute value of -3.5 minus R, which was 2.5. When you take -3.5 and you subtract 2.5, you get -6, total -6. I was about to put a decimal in there. -6. The absolute value of -6 is a positive 6. And we take a look, we go 1, 2, 3, 4, 5, 6. Okay, so that's how you can look at it at that number line. Now, we want to examine, I'm going to keep these up here, examine the measures of all 3 of these in example 2. What do you notice about their measures? Well, let's take a look. If you notice, the last one we did was the entire length from P to R. The other 2 were just the little portions. Oh, sorry, can't even see it. PR over here was the entire length from left to right, furthest left point to furthest right point. PQ was just this little portion. QR was this little portion. Well, if you take from P to Q and you add that from Q to R, you're going to get 6. So when we take PQ, okay, so we take PQ, we add this QR, we're going to equal that length of PR, the whole thing. So again, this is 1.5 plus the 4.5, and it all equaled 6. Okay? This is what brings us into our next postulate. It is called segment addition postulate. All this means is part plus part equals whole. So we're saying if B is between is a huge word to look at. You'll notice that later on. Between means I don't know where it is. It could be closer to A, it could be closer to C. It's somewhere between the two. It's not in the middle. We're not saying middle. We're just saying it's somewhere in between them. Then you add AB plus BC, and you're going to get the whole length. So if B, look, is between A and C, then from A to B plus B to C is going to equal AC. All right? And same thing, if you find out they add together, then it's between. But big thing right here is this part plus part equals whole. Okay? You'll see me writing P's and H, or P's and W's. So we're going to jump right into the algebra here. Okay? I'm going to have S is between, so I see, and that's a big word you're going to want to highlight. Okay? And you'll learn a little bit later why. You'll learn next a few notes from now. Notice how S is not in the middle. It looks like it's closer to R than it is to S. Okay? We never really assume, but it says it's between, not in the middle. So what we have here is we have part, RS. We have another part, ST. And then RT is the whole. So we do our part plus part equals the entire thing. So here we'll do P plus P equals W. The part plus part equals whole. So let's go ahead and take this. We're going to take our part, 2x plus 7. We're going to add our other part right here of 28. And we will set this equal to the whole, which was 4x. Now we will go through our process of solving for x, and we will figure out what x is. Noticing that they want us to find RT, so we will have to substitute in. So let's go ahead and start by finding, we have variables on both sides. We also have terms to combine. So I'm going to combine my like terms first before I start moving things around. So we're going to wind up with 2x plus 35, combine the like terms, equals 4x. I'm going to go ahead and I'm going to move my variable, subtract 2x from both sides, so these cancel. I have 35 is equal to 2x. Last step, we're going to divide both sides by that coefficient in front of the variable. We're going to find out that x is equal to 17.5. Now again, look at the problem. They wanted RT. So let's figure out RT from R to T, the whole, okay, was 4x. So all we're going to do is we're going to take that 4, we're going to substitute in, we're going to remove x, and we're going to put in that 17.5. When we do that, we're going to find out that the length of RT, when we multiply that out, is going to equal 70. Okay, so that's setting it up and then solving for that. All right. Now we're going to take a look at the next problem here. And we are going to have to draw this one out. Okay. So B is between A and C. So when we draw our segment, we're going to go ahead. B is between A and C. These are going to be our end points here. So we have A and we have C. B is somewhere between them. We don't know which little segment, A, B, or B, C. We don't know which one's bigger or smaller. Okay, so we just put it between. We're told that AC, which is the whole, is 14. And we see that BC, so from B to C, is 11.4. We want to find AB. So this is going to be our variable, our x right here. We need to find him. So again, with our part plus part equals whole. Here's your part, here's your other part, here's the whole. So we take our part, x, plus our other part, 11.4, we set it equal to our whole, 14. All we have to do is subtract that 11.4 from both sides. We're going to find out that x, also known as AB, our missing segment distance here, is going to wind up being 2.6. Okay, so whether we have to draw it, whether we have the algebra in it, we started off with the difficult part doing the algebra. Now, what we can do is we can use Pythagorean theorem to find the distance as well. So let's take a look at what this is going to look like. Okay, we're going to find AB. So we're going to find the distance from A to B using Pythagorean theorem. We're going to leave it in its simplest radical form. We haven't talked about how to simplify radicals yet. So we're going to use we're going to kind of reverse this because we're going to be looking for our hypotenuse. Pythagorean theorem. We're going to do c squared equals a squared plus b squared. We're going to kind of reverse the c squared there. So what we're going to do is here, we're going to take, doesn't matter which one's a and which one's b, but we're going to take our vertical and our horizontal distances here as a and b. Right here we see that our horizontal distance is 2, and we see that our vertical distance right here, if we count it, 1, 2, 3, 4, 5, 6, 7, 8 is 8. This is A and B. We are looking for C. Okay, here's our 90-degree angle right here. So we're going to have C squared that we don't know is equal to A squared, 2, so 2 squared, plus B, 8 squared. Then we go through our process. 2 squared is 4. 8 squared is 64. We're going to go ahead and do c squared equals 68. We remember with Pythagorean theorem, our last step is always going to be to square root. Now, it did say the simplest radical form. We don't know how to do that just yet. So when we do the our 2 square root of 17. We're just going to go ahead and plug. We'll just round this to the nearest tenth. We're going to wind up with approximately, we'll do our little approximate symbol here. That means approximately, squiggles, not equal, but approximately, 8.4. Okay? And if you count, you can't count diagonally. So you're just going to have to trust your Pythagorean theorem. All right? Next, let's take a look at finding your distance on a coordinate plane, which is exactly what we just did. We have another formula you can use, so if you don't have the graph to plug it into, okay? What's happening is you use your distance formula. Your distance formula, if you look, this is C, what we just looked at, okay? We had our horizontal and our vertical distance. The thing is, we're using the distance between 2 points. We're using that formula from the very, very beginning of the notes. But instead of having to do all this stuff and figure out the differences between y and the differences between x, we can use a very different version of Pythagorean theorem. Instead of taking the square root at the end, we can actually take that square root and put it over a squared plus b squared. So now we have c equals square root of a squared plus b squared. Now, when we do this, we have to look at your length and your distances. So we're going to be using two different coordinates, x1 and y1, x2 and y2. These are going to be our coordinates that we're going to have. Then we're going to find the distance, and the formula is, we're going to have a big old square root sign. Not sure how long this will take, but your formula is, you're going to, in parentheses, you're going to have x2 minus x1, parentheses, squared. So there's a, what you see right here, oh sorry, this is y, but plus, you're going to have your y2 minus y1 squared, all underneath that square root. Notice how x2 came first, y2 came first. x1 came second, y1 came second. You have to keep it in this order, and I'll show you an easier way to help do that. So here are our coordinates. I need to find the distance between these. So what I'm going to do is I'm going to label them x1, y1, x2, y2. So my first set of coordinates, here's x1 and y1, because it's the first set of coordinates written. So that's number 1. My second set, I'm going to label as x2, y2. So then when I go to fill in my formula here, I'm going to take this, we're looking for the length, the distance between these, so we just put d for distance. We're going to do the square root of, we're going to plug in x2, which was negative 2, minus x1, which was 2. Don't forget the squared. Then we have our plus, parentheses, y2, negative 3, minus y1, which was a negative 1, so I'm going to put another parentheses. So see, it's a negative 1, all squared. And then we take it step by step. You can't plug this all in the calculator at once. You've got to be super careful. You mess up on one little number, and you've got the wrong answer. So that's why I always suggest go through each little baby step. First thing, let's go ahead and let's solve what's in the parentheses. PEMDAS. Okay, negative 2 minus 2 is going to give you a negative 4. Don't forget your squared. Notice I'm leaving it in the parentheses, the big reason why. Plus, I have a negative 3 minus a negative 1 that turns into a plus 1. We're going to have a negative 2 squared. When you square any number, it will always be positive because this is a negative 4 times a negative 4. Negative times a negative is a positive. If you square a number in your calculator and it shows up as a negative, you need to go back and put these parentheses, okay, with the exponent outside of the parentheses. Okay? So then we'll go ahead and square them. Negative 4 squared is going to give you positive 16, plus negative 2 squared is going to give you a positive 4. Add those two together, you're going to get 20. And then whenever you take that square root of 20 in the calculator, your distance will round to the nearest tenth, will be approximately 4.5. Okay, just baby step by baby step. Now, when we're talking about segments being congruent and distances being equal, there are some very, very important things. When you have line segments that are the same length, they're called congruent segments. Okay? So if we take a look down here, lengths are always equal. Now, when we're talking about lengths, right here we got segments are congruent. I want you guys to notice the difference between not just the symbol, but the letters. AB for the lengths does not have a line over it because it means the length of AB. And same thing with CD, does not have the line over it, so we're looking at length. Notice how here we have segment AB is congruent to segment CD. I have a line, I have the squiggly line above the equal, and a line above CD, right? So we have that extra thing. Over here we don't. We don't have any symbols. We just have these two lengths are equal. Lengths cannot be congruent. Lengths are equal. Segments are congruent. Segments are not equal. Okay, so here's this to always refer back to. So we're not putting the wrong symbols in the wrong places. All right? Next, let's take a look and find out if these distances are going to be the same. I'm going to ignore the graph. We're just going to do the distance formula. Okay? So we take, first we want to figure out, well, it does say plot them, but we're going to take F and G. So these two, and we're going to take J and K. And we're going to practice using that distance formula. So this is saying segment FG, this is saying segment JK. So now I want to say the length of FG, and I'll start doing my distance formula here. So the length of FG, no symbol above it, is equal to, remembering our distance formula, okay, go ahead and write our distance formula up here. We have the square root of x2 minus x1 plus y2 minus y1. We need to make sure that we square them. Okay? So FG, go ahead and do our little square root symbol. Don't know how long it's going to be. Open up. Let's say this is x1, y1, x2, y2. Please label the ones and the twos. I cannot tell you how much that helps. Okay? We're going to take x2, which right here was 5, we're going to subtract x1, which was 1, and then put our exponent on the outside. Then it tells us to add. Open up our parentheses. We have y2 of 5. We're going to subtract y1, subtract 2, squared. Ooh, almost made it perfect size. Step by step, so we don't make any errors. We're going to go ahead and we're going to go ahead and solve inside the parentheses. 5 minus 1 is going to give you 4 squared, plus 5 minus 2 will give you 3 squared. Okay, everybody on board? Go back and rewind if you need to look at what we did. So now we're going to go ahead and square them. 4 squared is 16, plus 3 squared is going to be 9. We're going to go ahead and add those together, and we'll have the square root of 25. Now, what ends up happening is this is what we call a perfect square. The square root of 25 is 5. So this is the length of FG. No symbol above it. Here we're talking about segment. Here we're talking about the length. Okay, so we need to figure out if these two are congruent. So let's take a look at the next one. We have J and K. Here's x1, y1. Here's x2, y2. So let's look at JK. Go ahead and drag our little square root symbol. All right, follow our formula. x2, negative 1, minus x1, negative 4, squared, plus, hopefully I have some room, y2, which is a negative 3, minus y1, 0, squared. Follow the formula to a T perfectly. All right, let's solve in the parentheses. Well, when we have negative 1 minus a negative 4, well, that's going to come out to a 3. So we have 3 squared, plus negative 3 minus absolutely nothing, we have a negative 3 squared. All right. Then we're going to go ahead and square. 3 squared is 9, plus a negative 3 squared is still going to remain. So then we add those two together. We have the square root of 18, which we can already see the radicals are not the same. Our square roots are not the same, so we can already determine they're not going to be congruent. When we plug that into our calculator, we're going to get approximately, round to the nearest tenth, 4.2. So we look at these and we say, are they congruent? No. Because, and watch this, because FG is not equal to JK, all right, I'm going to introduce you guys to a shortcut of therefore. Since the length of FG is not equal to the length of JK, therefore, we can conclude that segment FG is not congruent to segment JK. Okay, that's going to be how we're going to write that out. All right, and that brings us to the end of our segment addition, or sorry, our segments and our distances.